everybody. Thank you for the invitation. So I will not try to make a review of the results from RPWS. I made some choice, which are biased, of course. Okay, assume that. So this talk is given, of course, on behalf of the whole RPWS team, and there will be pictures later. But first, let's start with the instrument. RPWS, so radio and plasma wave science, is an instrument that was made of a few boxes of electronics, a few cubic decimeters, a few kilograms. The boxes were made, half of them in the University of Iowa, and half of them in Paris Meudon Observatory for the high frequency part of the instrument, plus some contribution from Laboratory of Plasma Physics for the magnetic measurement. So there are also search coils at the other end of the spacecraft, here, the magnetic antenna. And the three big wires that you see here are the electric antennas. So we use these three metallic wires in order to pick the electrical signals from the waves, low frequency waves, and analyze them. And we use the search coils for the magnetic waves, magnetic component of the waves. And so the instrument in the box, you had a series of receivers. Basically, on the left here, you have the sensors, electric field, magnetic field, Langmuir probe. This, Jan-Erik Wallon will talk about that later. And then you have the various receivers that go from very low frequency, about 1 hertz, to the highest frequency was 16 megahertz, actually. So the high frequency part was made in Paris Observatory, all the mid and low frequency part in University of Iowa. And this produces, of course, not images, because in radio, the wavelengths we observe is tens of meters. The antennas are also 10 meters long, and so you cannot build images easily because the ratio lambda over d, as for any telescope, is very bad. Okay, but before coming to that, let me add that one peculiarity of the Cassini receiver is that it was extremely sensitive. This is in red, the sensitivity of the instrument compared to Ulysses, to Voyager, Galileo, and you see that it's really, really very, very sensitive, as sensitive actually as Ulysses, that went to much lower frequency and had very long antennas. Okay, with this electric and magnetic measurement, what do we measure? Saturn is here. Let's go back a little, and then let's look what is air, and this is what Andrew talks about. It's the magnetosphere. It's the environment of Saturn that is about 20 Saturn radii in the direction of the sun, and much longer in the opposite direction, that is filled with plasma, filled with waves, and in particular, in the polar regions, here we have the aurora created by the electrons hitting the atmosphere, producing ultraviolet light, and above that, producing radio waves. We have waves from the atmosphere, and so the objectives of the RPWS experiment were radio emissions, so primarily the Saturn kilometric radiation, the radio emission related to the aurora of Saturn. Then the plasma waves that are all across the magnetosphere and exchange energy with the plasma. Then the lightning from the atmosphere that also produce radio waves. And through the waves, you can also analyze the thermal plasma and diagnose the presence of dust. Okay, but then with, for example, Voyager or Galileo, the measurement we had, because we didn't do images, were just time frequency measurement of the intensity and polarization of the wave. And so in order to get source locations and information about the location of what's going on, we had to do a lot of indirect studies. In this case, we had a lot of discussion when building the proposal in the late 80s, actually, in order to how to have the best set of antennas that would allow to get some information about the K vector, about the direction of arrival of the waves. And I remember some meetings at the JPL with Don Gurnett and Bob Manning and some other people trying to decide if we would put the antennas at the top of the magnetometer boom, but this is a problem for the cameras, or on the spacecraft itself. And then I remember after a terrible meeting where it was decided to put the antennas on the spacecraft only, my colleague Alain Lecache had a good idea. He proposed actually to use 3 monopoles instead of 2 dipoles, and to correlate the signals between the 3 monopoles. And so be it, that's what we have done. And it turned out that when you have 3 antennas, so each monopole with its electric reflection on the spacecraft is approximately equivalent to a dipole. So we have like 3 dipoles. And when you correlate the signals between the 3 dipoles, you can retrieve the polarization and the direction of arrival of the wave if at a given time and frequency, one source is brightest in the sky, brighter than all the others. And so doing that, because the emission from the aurora are very sporadic at any time and frequency, it worked very well. And this is the kind of movies that we can build. So all the dots here are actual measurements during one of the flyby of Saturn. And to the right, you have the projection along a magnetic field on the planet. And you can see that at some point, we have magnetic field lines illuminated by the radio emission. So we can identify isolated field lines producing radio emission and see there, you see when we change the hemisphere, we change the polarization. So this was very important to understand the mechanism, and you have a movie of optical aurora at the same time, just for entertainment. So this was, we had a lot of these kind of images and movies that really gave, for the first time, instantaneous information about the location of the source. And so it was very important to understand the physics of this, because this was done only around the Earth previously. Then, because we had a lot of data, the RPWS was on the orbiter, so it worked for 13 years. And so we could do some very large statistics. So this is, for example, to the left, a statistics of the locus of the radio emission sources related to aurora, projected on Saturn. It's the high latitude. This is 50 degrees latitude, 60, 70, 80 degrees. So you have in dark the radio aurora, and you have nearby, at the same scale, an image made of several Hubble images added together that gives you statistically the UV aurora. And you see that the resolution is not the same, but the matching is very good. And if you even look at the profile along the aurora, the two profiles, the radio and UV, match very well. And so with RPWS, we really had a very deep investigation in the physics of Saturn's aurora and radio emissions, statistically at least. Then, okay, I'll come back to that. I should have reverted to item. Okay, no problem. You know that the magnetic field of Saturn is very much axisymmetric. It will be told together in more detail in another talk. This is some image at the top. Jupiter, for example, there are all kinds of tilts and magnetic spots. And so when the planet rotates, actually nothing changes because it's axisymmetric. And in spite of that, as soon as Voyager, it was found that the radio emission, the SKR, radio kilometric radiation, was very strongly modulated by the rotation of the planet at 10.8 hour, approximately 10 hours, 39 minutes. Okay. Then the things, and this is the usual way through which the rotation of the giant planets is measured, of the internal rotation, because the clouds are made of bands that go, each of them at their own velocity, their own speed. But with the radio emission, you're tied to the magnetic field, which is tied to the interior of the planet. So you measure the rotation. This is how it was done at Jupiter, Uranus, Neptune, and so on. Okay. At Saturn, okay, we had this rotation. But then in year 2000, using the data from Ulysses, there was a surprise. There was a paper in JGR by Gallopo and Lecache, some colleagues, that showed that from Ulysses, far away, you could observe actually the SKR, and they found that the period, the periodicity of the SKR was slightly different, 1% longer than the one measured by Voyager, and in addition, it seemed to vary. Wow, that's strange. And that was absolutely confirmed by Cassini as soon as it came close to Saturn, and furthermore, the instrument found some modulation in the plasma, the position of the magnetopause, the flapping of the current sheet, the aurora, everything basically in the magnetosphere varies with the rotation and at a variable rate. Well, this variable rate, 1%, is huge. It's 15 minutes compared to the Earth's rotation. The inertia of the planet does not allow the rotation to change by 1%. So there is something that must change. More complicated even, with later studies, we found that the SKR and the aurora and everything was not affected by one period of rotation variable, but two. There are two, actually, this is the time, the years, during the whole duration of the mission, with the various periods of higher latitude here. And this is a global image of what is measured as a function of the period of the radio signals. And you see that very often you have two periods, they change, they merge together after the equinox, and then they vary again. And if you separate the data by hemisphere, you find that these two periods are mostly related each to one hemisphere. And even in some hemisphere, you see the two periods. It was very complicated. So there was an awful lot of theoretical work trying to explain that. Variable plasma flow, variable magnetic cam, asymmetric rotated current systems, source slippage, Kelvin-Helmholtz instability. Well, finally, it's not totally solved today. Today, the modern picture is that the interior rotates at 10 hours, 32, 34 minutes, so slightly shorter than the radio emissions. This is related to the shape and the rings measurements. And there is magnetosphere, ionosphere, atmosphere coupling that makes the magnetospheric phenomena and radio emission to slip in a variable way, depending on the conductivity of the ionosphere that changes with season, for example, and changes between the two hemispheres, and that may be driven from the atmosphere. Not all the problems are solved, and if you give me a second Cassini, I'll buy it. Then coming back to the SKR, at some point, and mostly at the end of the mission, but still even in the middle, there were some close paths to Saturn at very high latitudes, and so Cassini could really go through the sources of radio emission. And this was extremely important because combining measurement from CAPS, from RPWS, from MAG, we could measure the radio emission, the plasma, the density and the energy of the plasma. This is the energy here with hot electrons, the currents. This image where the radio emission comes down to the cyclotron frequency local is extremely similar to what was measured at the Earth, for example, by Viking spacecraft. And by doing detailed studies that I cannot detail here, we found out that the electrons here measured at 6 to 9 keV were totally consistent for being the source of this radio emission, and the cutoff of the emission was totally consistent between what is observed and predicted. So actually with Saturn and RPWS, we had the first in situ studies of radio emission sources that we had only at the Earth before, and that now we have with Juno at Jupiter. So it was extremely important, and this allows to be transposed to now exoplanets and star-planet interaction, because we now know well the physics. So very briefly, lightning, a lot of lightning. This is the rotation of Saturn. So at each rotation, the storm system, identified in ISS images, would just produce a lot of lightning that would be detected in radio. There was even collaboration with amateurs that could observe the lightning from the ground. Lightning were observed from 2004 to 2013, and then nothing, in spite of the fact that the mission lasted for 2017 in perfect shape. It means that there are really huge seasonal effects. We are now almost half a Saturn year after 2013. And so we expect that the activity may resume, and we are ready to observe it from the ground. Because indeed, lightning were detected from the ground at the Ukrainian radio telescope UTR-2. It's this kind of signal, sporadic one. And we could even, with high resolution measurements, observe the dispersion of the radio waves through their trip from Saturn to us through the solar system plasma. There was a giant storm, as you can see here, of course. You could see that there was something special in 2010, 2019. This is the famous giant storm that made the cover of Nature. And we detected thousands of lightning during this storm, extremely energetic. We could measure the cutoff of the ionosphere of Saturn by propagation of this lightning through the ionosphere. We could measure a very special propagation effect. We could see the lightning in radio, even when the storm was behind the horizon. This was explained by some ray tracing programs that were built in the team, actually. Titan, measurement of the ionospheric profile, of course, especially with Langmuir probe and other kind of measurements. Titan orbits at 20 radii from Saturn. So part of the time, it's outside the Saturn magnetosphere. But most of the time, it is inside. When it is inside, it's connected magnetically. And this magnetic connection, similar to Galilean satellites and Jupiter, gives rise to wake, Alvan wings. And so it was modeled by several researchers. And it's quite interesting. There was no lightning detected from Titan. A lot was searched in detail, 0 lightning from Titan, which has some meaning. Dust, there was a question about dust. Dust was measured. The dust produces impact, very short pulses, electrical pulses in the instrument. And overall, you can detect the dust being detected in the spectra as this kind of events here when you cross the rings, actually. And there was population of the dust that were built from that, compared to the CDA experiment, and then the size, the mass of the dust could be studied, their interaction with the magnetosphere. There was a plasma cavity discovered inside the innermost ring, the D ring. Okay. So I cannot go well further. I cannot describe you the something of 300 or 400 papers built from the RPWS data. There was a nice report at the end of the mission. A lot of stuff I didn't talk about, low frequency emission, energetic events, and so on. The grand finale was a special moment where the trajectory of Cassini went to very high latitudes and very close to the planet. And so this was very, very interesting to observe. First, when you were grazing the atmosphere at the equator, or the ionosphere and the dust, and at high latitude, the SKR sources. And so a lot of studies in the sources were done, a lot of papers were done from that. Just a few words to end with the team. This is 34 years ago. I know Jan-Erik want to show the same picture, so I let him do the jokes on that. This is me. Jan-Erik is maybe somewhere here, or maybe next one. So the PI, Don Gurnett, Bill Kerr, the deputy PI, and a lot of people who were young at that time. Some of them passed away since. Bob Manning here was our lead engineer in Meudon who built the high-frequency receiver. This was at the launch, so 6 years later. And this was 20 years later, with many people still here and new people coming in, of course, from Meudon and from other places. So there was a huge collaboration. This was a very long-term, very, very exemplary collaboration between the US, Europe, Japan, now China. We had a lot of Earth-based support in observations. There were annual team meetings in Iowa, special meetings, and all is excellent memories, actually. The data from RPWS, as from the other instrument of Cassini, was very well archived. And this database allows now to continue to produce a lot of studies that continue every year to come out from this data above a lot of topics in the magnetosphere of Saturn. I must emphasize that one of them, Xiyuan Wu, a student of a former COI of Cassini Shengyi, who is now in China. Xiyuan Wu is now a postdoc in Southampton. He's doing a terrific work at analyzing this data. And for example, recently, we found for the first time the harmonic emission, second harmonic of the SKR that was never spotted except at the Earth. And this bears a lot of significance to the emission mechanism and the plasma physics of this. And it's really interesting. So because this was supposed to be a celebration, so I wanted to have to end on an entertaining slide. And so we made some outreach with RPWS because we didn't have very nice images. We made sound instead by transforming our dynamic spectra in sound. And so this is some kind, for example, of skip to some ghostly plasma waves. Some lightning in the atmosphere. And I skip the last one, you come to see me. Now, after that, well, we have Juno at Jupiter that does the same physics, ground-based observation of lightning, moon-based observation soon of this radio emission, and a lot to come. And when I came here, I was at the station Metro Montparnasse, and there is a nice exhibit that honors actually and showcase space mission, and Cassini is part of them. So I finish with this slide. Thank you. Thank you.
We have time for a short question if there is any.
So comment about the lack of lightning on Titan. Of course, there is convective activity, but the condensate is nonpolar. It's methane, so it's very difficult to build up charge separation during collisions. And so we expect to have thunderstorms without the thunder.
Thank you one more time.